and I want to start.
So starting with theoretical quantum mechanics and finishing with the real device. So I'd like to start by thanking all my collaborators over the years on nanomechanics and the funding, and of course the organizers, Dani and Yoram, for inviting me to talk here, and also to thank them for a wonderful workshop. It's so nice to come to a workshop and not have to worry about anything. But one of the things that I was worried a lot about last year, and I think is tremendously improved, is the presentations of the talks. Last year I got a lot of criticism about the talks that the physicists and the engineers gave. And so in preparing this talk, I decided I would give a completely different version than the talk I ordinarily give. This is PG-13, which in the American movie rating system means parental guidance. So there might be some offensive language here and there, but if you're this age, you can stick around and listen. As always, you know, if you are less than 13 and you are forced to watch only these movies, you know that you're missing a lot because you can't see all the sex and violence and so on. So you are going to miss a lot of the actual stuff that's going on. And if you want the R-rated version of the talk, that'll have to be a seminar somewhere in a different setting. So what's my plan? So I'm going to tell you about one of the most, I think, complicated projects that's going on in my group, which has to do with quantum nanomechanical systems. So I'll start by giving you a quick introduction to these nanomechanical systems. They usually have an electronic component to them, so they're generically called nano-electromechanical systems, or NEMS for short. Then I'll have to give you some very, very quick and brief overview of quantum mechanics, and then I'll tie the two together and try to convey some of the excitement that we have in working in this emerging field. And so, you know, there'll be maybe 25 minutes of introduction and a few minutes about the actual topic. And you should remember that this is the PG-13 version. For some reason, the image didn't come out here. Now, let me start with the quick introduction to these, to nanomechanics, or nanomachines, which is one of the promises of nanotechnology. And of course, when we talk about nanomachines, we immediately think of these images that appeared in Scientific American and various other publications of little nanorobots, or nanobots as they're called in the science fiction literature. They do a lot of great stuff for us. They service our blood cells, but they can also become very dangerous if you're not careful. By the way, if anyone has a copy of this book, I'd love to borrow it. I haven't read it yet. But this is not quite what we're talking about. What we're talking about is the very natural progression in the miniaturization of machines. Now, machines on the micron scale, so-called micro-electromechanical systems, or MEMS, have been around for quite a long time. And these are machines whose dimensions lie within these 3 decades on this scale. And so it's very, very natural to try to continue this miniaturization process and move over to machines whose dimensions are on these scales. Now, MEMS have a tremendous number of applications. They've been reviewed in many places. This is just one example. And we have experts on campus who work with MEMS, Yael Khanin and Slava Krylov. So if you want to know more, talk to them. But this is really only a partial list. There are many, many more applications. If you look at these machines on the micron scale, they're actually quite nice. You know, you can really see these nice motors with gears and stops. Here through the pinhole, what you're seeing is a little mirror, and there's a motor behind the mirror that can change its orientation. So these are really very fancy machines. In fact, the images I like the most are these images where you see these giant bugs. They're, of course, less than 1/10 of a millimeter in real size, but compared to these machines, they look like monsters. Now, what do nanomechanical systems look like? Well, nanomechanical systems, they're much smaller, and they're also very, very basic compared to what we've used to seeing in MEMS. And mostly what we have in the nanoscale are resonators. So these are devices of various design and geometry. You can see here different designs. And what they can do is that they can vibrate. Sometimes we want to work in a situation where indeed they vibrate, and what is important for us is the frequency in which they vibrate, and we can monitor that very accurately. And sometimes they just work in a deflection mode. You just need to push them once, and that does something for you. You can see different geometries, as I said, just simple beams, like a string in a violin. This H-shaped, which was designed for some purpose. This is a torsional resonator. It's something that goes like this. And what you see here in this image is one of the first images of a single carbon nanotube that was suspended. There's nothing holding this nanotube from beneath, so it also can vibrate and operate mechanically and do hopefully something useful for us. So, as Eran said earlier today, small is good. And for all the reasons that nanoelectronics is good and miniaturization in electronics is good, miniaturization in mechanics is, of course, also good. I won't go into the detail. Clearly, the smaller, the better. But is this all there is to it? So are NEMS just simply smaller version of MEMS? And the answer immediately is no. Otherwise, I wouldn't be standing here as a theoretical physicist. So let me give you a number of reasons why I think that NEMS are not just smaller. Of course, they are smaller, but they have additional benefits to them. First of all, in some sense, they are the smallest that there is. If you look at certain devices like sensors that people are thinking of making out of these little machines, one of these sensors will measure charge. Now here is one of these torsional resonators, similar to what I showed you earlier. And the idea here is that the frequency of this torsional resonator, because the mass of this object is so small and the frequency is relatively high, just very tiny amounts of charge on this finger will change the frequency of this resonator just by applying an electrostatic force onto it. And measuring different small changes in frequencies is something that is relatively easy to do. So one is hopeful that with these kinds of designs, one will be able to measure the electrostatic force of a single electron. And as you know, that's the smallest charge one can have. Similarly, one might hope to measure the magnetic force of a single spin. Now, this has actually already been done for a single electron spin, and this is an experiment by Dan Rugar's group at IBM Almaden about 5 years ago, where they actually managed to show that the spin of a single electron changed the frequency of this vibrating cantilever in a substantial way that one was able to measure. So again, along these lines, do mass spectroscopy of single molecules. Now, excuse me for this crude depiction of this, but again, the idea is that you have a whole bunch of cantilevers, and you can actually functionalize them. So you attach something to the end of the cantilever. On the other end of this long molecule, there's something that likes to bind to a specific type of biomolecule. And once that molecule binds, again, the mass of the molecule is sufficiently large to change the frequency of this cantilever, and you can pick it up, and you can do mass spectroscopy on a single molecule level. You might want to measure the heat released by a reaction undergone by a single molecules, and so on and so on. So it really is the ultimate precision. It's not just smaller. It really is the smallest one can hope for. The second thing, of course, and this is something that many of you are familiar with, is that at the nanoscale you can combine standard top-down fabrication schemes where you take a block and you chop it off, and at the end you get some sort of a device with bottom-up self-assembly. Like these elements that I showed you earlier, the carbon nanotube, that is something that grows by itself. It can grow over a trench, like in this example, or in some cases you grow it elsewhere, but you pick it. You pick it up with a tip. This is a standard micron-sized tip, but at the end of this tip, there's a bundle of carbon nanotubes, and this was at some point called the nanopencil. It was able to make indentations with a nanometer scale resolution. So this is another added benefit. Another benefit, which again is important to this audience, is that it's a perfect interface at this length scale with biological systems. And this actually goes both ways. So both sides can benefit from this point. So I already showed this idea of measuring single biological molecules, and that's because at the nanoscale, these machines are smaller than a cell, but not much bigger than a single biomolecule. So this is nanomachines serving biological research, if you want. But things can go in the other way, because the biological world, through evolution, has created a lot of machines at the nanoscale. So we might actually look at the machines that evolution created and imitate that. Or maybe if we don't want to imitate that, at least we have a proof of principle that something can be done on that scale. So here you have some sort of a rotary motor that moves the hairs of this E. coli bacterium and allows it to swim. So this is a kind of a motor that exists in nature. I'm not sure that we want to imitate that, but at least we have a proof of principle that something like this is possible at this scale. Of course, as all of you know, nano is much harder than micro. It's not just smaller. It requires a lot more effort. It requires more effort to fabricate the devices, to reproduce them, to get identical devices day after day, and of course to interact with them as well. And I'm sure that many of you have seen this cartoon, or maybe have actually lost a device on a chip and looked for it for a couple of hours. This is a real problem that requires ingenuity. And finally, and the reason that I'm standing here, is that I think it gives rise to new physics, or at least gives us an experimental handle at checking various physical predictions that we didn't have a handle to prior to these nano systems. So I want to talk about quantum nanomechanics, which means that I need to give you a very, very brief introduction to quantum mechanics. And I'll start by saying that quantum mechanics is probably the most accurate and successful theory in the history of science. Some people might even go as far as saying that it's the greatest intellectual achievement of the 20th century. And I'm actually quoting someone here. And this is taking into consideration all the beautiful art and literature and discovery of DNA and sequencing of the human genome. It truly is a fundamentally important theory. The downside is, or maybe the upside for people like me, is that, I'll tell you later, is that it's a very, very strange theory. Nothing like we've seen before, and nothing like we've seen after, I think. Feynman, who was one of the greatest physicists of the 20th century, is always quoted as saying, I think I can safely say that nobody understands quantum mechanics. So if you don't understand quantum mechanics after this brief overview that I'll give you, don't feel bad. It truly is a very, very strange theory. In fact, I think this has been used as an excuse for students who failed their quantum mechanics exams over and over. But let me try to describe to you some of the main features of quantum mechanics and try to convince you that it truly is a very strange theory. First of all, the first statement is that everything is quantized. What that means is that physical quantities that we're familiar with come in little pieces, in little chunks, and you cannot subdivide these chunks. These are these particles. Now, some of these particles we're really used to, like electrons. We know that an electron comes with a particular electric charge, and there's no smaller charge than that. This is an elementary unit. But not only matter is composed of particles, radiation is also composed of particles. And so this might be a bit offensive, but not too bad. Light is made out of particles that we call photons, particles of light. But the strange thing is, really, not that everything is made out of particles, but that the description of all of these particles, whether electrons or phonons or any other particles, is through something that is called a wave function. So we don't describe the particle itself, we describe something else and use that to say what the particle is going to do. Now, one of the immediate consequences of that is that in quantum mechanics, you cannot determine the outcome of an individual experiment. All you can determine are probabilities of different things happening. And the reason for that is exactly because we don't describe the particles as particles like we were used to in classical physics. In classical physics, we start with a particle, we say that it has a certain position and a certain velocity, and we ask at a later time, if we know what forces are acting on it, where it will be with what velocity. This is a standard question in classical mechanics. In quantum mechanics, you start with the initial conditions of the particle, and you describe them with a wave function. Now this wave function, something abstract, we're not going to go into detail, is something that we can very accurately say what it will do at a later time. But at that later time, when we want to decide, given the final state of that wave function, where the particle is, all the information that the wave function is going to tell us is the probability of finding it here and the probability of finding it there. For a given experiment, we won't be able to tell what is going to happen. Now, to make things even worse, in quantum mechanics, there are certain pairs of physical quantities that cannot both be measured accurately at the same time. This is the so-called uncertainty principle. So as I said, in classical mechanics, we start by stating exactly the position and the velocity of the particle, and we use that to calculate what will happen afterwards. In quantum mechanics, we cannot specify exactly both the position and the velocity of the particle. It's just impossible. If I know exactly where the particle is, I have no idea with what velocity it's moving. If I know exactly what the velocity of a particle is, I have no idea where it is in space. This really makes life quite hard if you want to predict things. But the most really bizarre aspect of quantum mechanics is this statement here. It's the statement that physical quantities, like position, do not have actual values unless they are measured. Okay? It's a statement that there is no objective reality. There's no quantum objective reality that exists out there without anyone interacting with it. Only when you interact with a quantum system, you look at it, you measure it. I put measured in quotes because there's a lot of discussion over what is measurement in quantum theory. But only when you measure it do these quantities get their actual values. This is truly the weirdest aspect of quantum mechanics. But the reason that this all looks so weird to us, even though this is how we believe the universe is described, is because it applies on very, very small scales, on atomic and molecular scales. On our scales, it does not apply as far as we understand, and so we're not used to it. So everything I said up until now should sound extremely weird to you. Now, one of the people who really worried about these aspects of quantum mechanics was, of course, Einstein. And about the probability, he said, quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he does not throw dice. So Einstein really said that this is not a complete theory. It's not the final word because he didn't believe that the real world is described by probabilities. It's just the inability of the theory to say more than that. On the notion of reality, he was really, he wrote about that for years. And he said most physicists simply do not see what sort of risky game they are playing with reality. Reality is something independent of what is experimentally established. Reality is there whether we look at it or not. And the wonderful quote from Abraham Pace is that we often discussed his notions on objective reality. I recall that during one walk, Einstein suddenly stopped, turned to me, and asked whether I really believed that the moon exists only when I look at it. Of course, this brings it to an absurd, but this is the statement. This is really the statement. Now, other people didn't worry about these questions too much. One of them is Pauli. Pauli said one should no more rack one's brain about the problem of whether something one cannot know anything about exists all the same than about the ancient question of how many angels are able to sit on the point of a needle. But it seems to me that Einstein's questions are ultimately always of these kinds. So Einstein is a nudnik. He really shouldn't bother us with these kinds of questions. Niels Bohr answered Einstein in a much more serious way, and they had year-long debates over this notion of reality. And Niels Bohr said there is no quantum world. There is no objective quantum reality. There is only an abstract quantum physical description, this wave function. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. So we shouldn't really care about whether there is an objective reality. Our role is to say what we're going to see if we're going to look at things. Philosophers can worry about the other aspects. So having said all that, of course, I want to raise the question again, does quantum mechanics apply on large scales? Of course, Einstein said the thing about the moon, but Schrödinger came up with an even nicer absurdity that comes out of a statement that quantum mechanics applies for large objects. Because of time, I won't go through the details of this famous proposition of Schrödinger, but basically there's a closed box, and in this box there's some quantum process that happens with a 50% probability that it will happen and a 50% probability that it will not happen. But for a given experimental setup, we don't know if it's going to happen or not. In one case, a bottle of poison will break and a cat will die. And in the other case, nothing will happen and the cat will live. And the question is it really reasonable to say that the cat is described by a wave function, which is some sort of we call it a superposition of either being dead or being alive. And until we actually open the box and look inside, it doesn't have, there's no sense in talking about the livelihood of the cat. That's basically the statement of quantum mechanics. So the question is, well, if not, then why? And it turns out that most condensed matter physicists, and Tony Leggett wrote a lot about this issue, say that it does apply on all scales. So there's really no limit on the validity of quantum mechanics. But what happens for large systems is that they're so large and composed of so many degrees of freedom that they're always interacting with the environment. And interacting means that something is measuring this system all the time. And so it loses its so-called quantum coherence, its quantum weirdness, just because it's a big system interacting with an environment. It's a process called decoherence that was mentioned yesterday in one of the poster presentations. On the other hand, there are others, like Roger Penrose, who's a cosmologist, who say that the mere fact that something is big is already enough to invalidate quantum mechanics, and this has to do with gravitational forces and the theory of general relativity. This is a very complicated argument. I'm not sure I understand it all the way through, but they're different. I want to just emphasize the fact that we don't really know, because this has never been tested. So the question is, can NEMS be quantum? NEMS are not very small. They're not atomic scale. They're not like cats. They're somewhere in between. And now we have a system in which we can try to see, is something intermediate going to be quantum mechanical or not? So let me tell you a little about how we put these things together. And the question we should ask is really, how big are these NEMS devices compared to the quantum scale? And the quantum scale, at least in our universe, is set by the Planck constant, which in ordinary MKS units is a tiny number. It's 10 to the minus 34. And so we want to ask, how big are our NEMS resonators compared with this universal value? And so we want to have something with a dimension of length. If I have a resonator vibrating sideways, this will be the width of the resonators, d squared, the mass of the resonator, and the frequency of the vibration. That will give me the inverse time. And so if I very crudely calculate these numbers for standard kind of NEMS beams, what I get is 10 to the minus 26. And if I look for these numbers for nanowires, like nanotubes, then I get an even much smaller number, 10 to the minus 31. So if I compare that to Planck's constant, these systems are 1,000 times bigger than the quantum scale. And these are already 100 million times bigger than the quantum scale. So hopefully already here we'll be able to make some progress, and if we do make some progress here, we'd be very happy to go on to larger systems. So what do we expect to see if we eventually manage to see quantum behavior in a large object? Maybe not a cat, but something that's approaching the size of a cat. The first thing, if we're looking at resonators, is again, everything is quantized, as I said, and elastic vibrations are also quantized. So this is my first equation in this whole theoretical physics talk. This is the energy that I can find stored in a vibrating resonator. And this energy is always an integer number n plus 1/2 times this basic unit. The basic unit is composed of this Planck's constant, h bar, and omega, the frequency of vibration. So if I add energy to this vibration, I cannot add it in a continuous way. I will always add these quanta of h bar omega. I will add particles of vibration, particles of sound. These are the R-rated phonons. Okay? So this is for a different talk. but I am talking about the ability to see these particles of sound, this quantization, and the question is, how will I be able to see this and all the other weird quantum behavior? Superposition of a resonator here, a resonator like this, with a 50% probability of being here and a 50% probability of being there, and all the other strange things. How much time do I have? 5 minutes. Okay. So, if I want to be able to resolve jumps in energy of this amount h bar omega, then one of the things that limits me in this energy resolution is thermal fluctuations. If I have a resonator inside some thermal bath, then it will be constantly kicked by other degrees of freedom. This is like the Brownian particle in the fluid that's constantly being kicked by fluid particles. A similar thing happens here, and so the energy of the particle, it gets energy and loses energy all the time, will not be very sharp. It'll be smeared out. So, of course, I want omega to be as large as possible so that these jumps will be as large as I can make them. And in 2003, we had at least a nominal breakthrough where these mechanical resonators were recorded at 1 gigahertz frequencies of vibration. Okay, this is not electronics. This is a whole mechanical beam moving simultaneously at a frequency of 1 gigahertz. Now, we've gone beyond that ever since, but we are in this range now. And if we compare mechanical energies, this h bar omega, with thermal energies, and we measure thermal energy in units of Boltzmann's constant times the temperature, then if we are at 1 gigahertz, then below 50 millikelvin, the thermal energy scale becomes smaller than the mechanical or the quantum energy scale. Now, 50 millikelvin is something that Yoram can produce in his lab, right? No? Not yet? 100? Okay. But definitely people around the world can achieve these temperatures, and people can achieve these high frequencies, but putting everything together in one experiment, of course, is extremely hard. There has been some progress. I won't go into the detail. We are getting closer and closer to being able to see this, but it's going to take a long time. I think that every improvement by a factor of 2 takes a fixed amount of time. It's something like inverse Moore's law. So it will take a while. So the thing that we asked ourselves, and this is the 3 minutes that I tell you about what we do, since all of this is very hard, so really seeing, quantum mechanics all the way to test all these weird predictions, we asked the simpler questions. We asked, can we just observe the dynamics of a single NEMS device, one of these resonators, and see, just by looking at what it does dynamically, a transition from classical to quantum behavior? Okay? We're asking, are there clear experimental signatures for such a transition? Let me clarify. So we want to observe, starting from a classical object, we want to observe the first quantum deviations away from classical dynamics as the system cools down towards this quantum regime. So we don't want to be at a temperature which is extremely small so that we can already resolve these jumps. We want to start cooling and say, at one point, do we start seeing deviations from what is predicted by classical mechanics? How much time do I have? Okay, so let me skip this. It turns out, for various reasons, that we cannot take just a simple linear harmonic oscillator. We need to look at a nonlinear oscillator. This is an oscillator whose frequency changes if we drive it stronger and stronger. It doesn't have a fixed frequency. But when we do take such a resonator, what we do to see or compare is calculate numerically on the left-hand side what that resonator would do if it behaved according to the laws of quantum mechanics. And on the right-hand side, ask, what would this resonator do if it behaved according to the laws of classical mechanics? Now, what is plotted here, this is somewhat R-rated, is dynamics in what is called phase space. This axis is position, and this axis is momentum or velocity. What we have on the left is something that expresses the wave function that I talked about earlier. It's something that is smeared. I don't know exactly where I am in position, and I don't know exactly where I am in velocity. I have this probability. If I project this image down here, then this is the probability of where what the position x of the particle would be if I try to examine it, if I try to measure it. This is the probability distribution. What I have here is a lot of points in classical phase space, and again, if I project them down, I obtain something with a similar probability profile. Okay, the scales here are not identical. Now what we do is we run the dynamics of this system. Again, I'm stopping it. On the left, we have quantum mechanics. On the right, we have classical mechanics. On the right, we just see the probability distribution having started with that blob, what happens later on. In classical mechanics, for every dot that you see here, we know exactly deterministically to say what it's going to do. On the left-hand side, you see that we have something that at least starts, at least the blue region, starts very similar to the classical one, but clearly they're what we call quantum interference pattern that appear here in between. Red are negative values, and this is something that cannot happen classically, a negative probability. There's nothing like that. But on the bottom we have probability distributions. Let me run this through and convince you that this is already very different. This is what we will see if our resonator is classical. This is what we will see if the resonator is quantum mechanical. And here we took the two energies to be identical. So here kT is equal to h bar omega. Thermal energy is the same as mechanical energy. Okay, but I want to see the first deviations. Maybe I can raise the temperature. I don't have to be as cold as this and still see differences from classical to quantum. So now kT is now twice h bar omega, twice the quantum energy. And let's see what happens here. Again, at early times, very similar behavior of the blue backbone, but we do get these interference patterns. We do get a different behavior on the left than we have on the right. This simulation takes a little, it's a movie. It's not calculating it on the spot, of course. It takes a little longer, but let us run through it, and you'll see that the classical resonator has basically two probability distribution peaks. If we perform this experiment very, very many times, say 1,000,000 times or 1,000 times, then we can build a histogram of where we found the resonator when we looked at it. And if it's classical, we will find this kind of a distribution. The quantum distribution is quite similar to the classical one, so it also has these two maximum points where the classical one has maximum points, but it's not as enhanced as in the classical case. In fact, in the quantum case, there's a region here where there's a finite probability of finding the resonator at the end of the experiment, whereas classically, there's no way that the resonator will be there. So what's happening here is that the system, the classical system, is stuck either here or there. The quantum system can switch between these two positions, and I have a finite chance of catching it while it's switching from here to here. So we propose this idea for measuring initial first deviations from classical behaviors, hopefully not so long in the future, so we don't really need to cool down as much as we did there. Let me just summarize. I hope I convinced you that NEMS are not just smaller MEMS. They're really a whole new world in terms of their physics. I hope I gave you some indication of really how strange and bizarre quantum mechanics is. In fact, I have a PG-13 talk about the debates between Einstein and Bohr. If you like, I can come and give that talk. It's more like a class. It's a 2-hour lecture. And I told you a little about quantum NEMS, and I think they're just around the corner. So we're very excited about these systems. And if you want to hear the R-rated version, as I said, that's a seminar and full of equations, I promise, and a lot of details. Thank you.
One quick question.
I'll answer.
יכול לתאר את המעבר, כביכול, המעבר מיוצב של מה שחלטני קלאסית למען אחרת קוונטית, האם אתה יכול לתאר את זה במונחים של פייסבוק, מעבר חלק?
Okay, so the question is this transition from classical to quantum behavior something analogous to a phase transition? And I think we really don't understand how this happens so deeply and fundamentally that trying to say more than that, like an analogy with phase transitions, would be a difficult thing to say, although I believe it is not. I don't think it's a phase transition. The way I describe it here, I really, and this is now an expectation, it's based on belief more than other things, that it's a gradual transition. As we cool the system down, I haven't mentioned anything about insulating the system from the effects of the environment. So we have to manufacture a system that would be as insulated as possible from the environment, as high in frequency as we can, and then lower the temperature. And then at some point, as we lower the temperature or make our devices smaller and smaller, at some point we'll start seeing quantum mechanics. At this point, it's just a gradual, inch by inch walk towards this regime.
The classical analog of Raman scattering is Doppler shift. You see symmetrical sidebands of the main radiation. Now, can you predict whether you will see transition to quantum Raman spectroscopy in such cantilevers?
So I don't think you need mechanical systems to, small mechanical systems to say that. Let me try to say, okay, so a lot of properties of light can almost analogously be explained in quantum terms and in classical terms. Many cannot, but many do. And the reason is that in the case of photons, the quantum mechanical equation that governs the dynamics of a photon is the same equation that governs the dynamics of classical electromagnetic waves. It's the standard Maxwell equations. Whereas for electrons and matter, we have a tremendous change between Newton's equations and the Schrödinger equation that governs the dynamics of the wave function. So in the case of light, I think that many times you will see something that is equally described in terms of a quantum mechanical and a classical description. I think an aspect of Raman scattering that you won't be able to describe classically, but I'm not quite sure how you're the expert, not me, how you would measure it, is that in the quantum mechanical description, you don't really care whether your matter absorbed the photon first and then emitted the second photon. Quantum mechanically, it can live in this weird state where first it emitted a photon, it generated this energy of the photon, and then very quickly absorbed another photon to fix this problem.
It's really the occupancy number of the quantum states.
Yeah, but that's only one half. But that's only one half of an H bar. That's.
So let's keep this discussion for the later.
Yes.
The next speaker is Boaz Almog, who's going to talk about the long range treatment,
We shortened the title, so triple insulator matters. A little bit simpler.